Welcome to Talk Tensors, a professional machine learning academic paper summarization podcast.
We are so thrilled to have you joining us today.
Yeah, we have an incredibly special deep dive lined up for you.
We really do.
Our mission today is to explore a truly, just a seminal paper.
Absolutely seminal.
We are going to unpack a piece of research that fundamentally shifted how neural networks perceive information.
It proved that sometimes the absolute biggest breakthroughs come from looking at the spaces between the data.
The spaces we usually just skip right over.
Exactly.
So whether you are a machine learning practitioner looking to optimize your models,
or just intensely curious about how artificial intelligence actually visualizes the world.
Right. Today's deep dive into the classic Squeeze-and-Excitation Networks paper will give you a profound aha moment.
It definitely gave the whole industry one.
We are talking about the architecture that won the massive ILS-VRC 2017 image classification competition.
Published by Jihu, Li-Shen, Samuel Albany, Gang Sun, and NY Wu.
It really is a watershed moment in the literature.
It is. And to truly appreciate what this paper accomplished, we have to travel back in time a bit.
Set the historical stage.
Right. So the year is 2017.
A wild time in deep learning.
It was. And if you look at the computer vision community at that specific moment, researchers were absolutely obsessed with spatial relationships.
Just totally hyper-focused on the spatial side.
The prevailing wisdom was basically that if you wanted a better model, you needed a deeper model or a wider model.
More layers, more filters.
Yes. We saw the rise of VGG nets, which proved that stacking more and more convolutional layers improved representations.
Yeah.
We saw the Inception family of architectures.
Those introduced multi-scale processing, right?
Exactly. Looking at different size spatial windows simultaneously using parallel convolutions.
And of course, ResNets.
Right, ResNets. They use residual skip connections to allow networks to become incredibly deep.
Without the gradients vanishing during training.
Which is a huge deal.
Yeah.
But almost all of this innovation was overwhelmingly focused on the spatial component.
Staring at the pixel.
Yes, trying to enhance the quality of spatial encodings. Researchers were constantly asking, how do we better look at specific parts of an image?
Right.
How do we map the physical relationship between, say, a pixel in the top left corner and a pixel in the bottom right?
Okay, let's unpack this.
Let's do it.
Prior to this paper, improving a neural network was basically like upgrading a digital camera's megapixel count.
That's a great analogy.
You just want a sharper, higher resolution image.
Right.
That is a purely spatial focus. You want more detail in the X and Y coordinates.
You want to see the crisp edges of a leaf.
Or the precise curve of a car's tire. You are zooming in on the physical layout of the pixels.
You're tweaking the receptive fields, playing with dilated convolutions.
All to capture better geometric features.
But what this paper did was entirely different.
It really was.
It shifted the paradigm from the spatial dimensions to the channel dimensions.
So the authors of this paper decided to pivot away from that spatial obsession.
They looked at channels instead. The core thesis of the Squeeze-and-Excitation paper is that standard convolution operators inherently entangle spatial and channel information.
Which sounds complicated, but...
Think about the mechanics of a standard 2D convolution.
Right.
A filter operates over a local spatial window, let's say a 3x3 grid.
It's a tiny little box.
But it spans across all the input channels. It computes a weighted sum over both the spatial neighborhood and the channel dimensions simultaneously.
Right, they get mashed together.
Because it just sums them up into a single scalar value for that specific spatial location in the output feature map. The relationships between those different feature channels are completely implicit.
Highly localized.
Very localized. There was no mechanism in the network to explicitly model the dependencies between channels based on the global context of the image.
And that structural limitation was effectively holding the entire field back.
It was preventing them from capturing more complex global semantic relationships.
Which brings us to the breakthrough metric of this paper.
The fun part.
This wasn't just an interesting theoretical exercise. It was a total demolition of the state-of-the-art benchmarks.
They wrecked the curve.
This squeeze-and-excitation architecture formed the foundation of the winning entry for that ILS-VRC 2017 classification competition.
The ImageNet competition.
Right. They crushed the top 5 error rate down to 2.251%.
Which is wild.
Just to put that in perspective for you, that was a staggering 25% relative improvement over the winning entry from the previous year.
A quarter of the error wiped out.
In the world of ImageNet benchmarking, where researchers spend months tweaking hyperparameters for 0.1% improvement.
Right, a 25% relative leap is Phenomenal.
It was a massive leap, particularly because the architectures they were competing against were already highly optimized.
To understand how they achieved that, we really have to look closely at the methodology.
Let's get into it, starting with the core problem with standard convolutions that we briefly touched upon.
Let's look at the math simply. In a standard convolutional layer, the filters operate with a local receptive field.
Like looking through a straw.
Exactly. A single unit of the output feature map can only see the information inside its localized spatial window.
Right.
It has absolutely no idea what is happening in the rest of the image.
So what does this all mean?
It means the network was literally missing the forest for the trees.
Because each filter was trapped in its little local bubble.
Right. The network couldn't dynamically prioritize which feature channels were actually important for the specific image it was analyzing as a whole.
It was just applying the exact same local logic everywhere.
Equally, without any overarching context.
So if we have a channel that acts as a strong detector for fur,
right, and the image is mostly sky and ocean,
a standard convolution doesn't have a mechanism to universally suppress that fur channel based on the global scene.
That is the exact friction point the authors identified.
And that leads us to their elegant three-step solution.
Step one is what they call the squeeze operation.
The squeeze.
Which is essentially a global information embedding.
Okay.
Since the local filters can't see the big picture, the authors force the network to create a summary of the big picture.
How do they do that?
They do this using global average pooling.
Right.
Mathematically, they take the entire spatial dimension of a feature map, the height multiplied by the width,
a whole grid,
and they pool it into a single scalar value for each channel.
So if you have a feature map tensor with dimensions h by w by c,
the squeeze operation collapses the spatial dimensions.
It just squishes them down.
It computes the average value across all those spatial pixels for each channel individually.
Okay, so what are you left with?
What you are left with is a 1 by 1 by c descriptor.
Just a single vector.
Exactly. A single vector that represents the global distribution of the feature responses across the entire image.
I love the analogy of a crowded room for this.
It's a great way to picture it.
Imagine you walk into a massive, noisy networking event. There are hundreds of people having different conversations. The squeeze operation is like taking a panoramic snapshot of that crowded room to gauge the overall mood.
Before you engage.
Right. Are people laughing? Are they arguing? Is the lighting dim or bright?
You get the vibes.
You do that before you decide which individual conversations or channels you want to actually tune into.
Exactly.
You are aggregating the global context, so you aren't just reacting blindly to the localized spatial window immediately in front of you.
That is a perfect way to conceptualize it. It provides a global receptive field.
So now we have the snapshot.
Right. Once the network has that panoramic snapshot, that 1 by 1 by c descriptor vector, it moves to step two.
The excitation operation.
This is an adaptive recalibration mechanism.
Okay.
The network takes that squeezed vector of global information and passes it through a small bottleneck architecture.
A bottleneck.
Yes. This bottleneck consists of two fully connected layers wrapped around a ReLU nonlinearity.
Two FC layers.
And what's fascinating here is the specific architectural choice they made regarding the dimensionality reduction ratio.
Which they denote as R.
Right, R. The paper defaults this ratio to 16.
Well, looking at the architecture, they're adding two fully connected layers to every single residual block.
Every single one.
Fully connected layers are usually notorious compute hogs. How is that not destroying their parameter and GFLOP budget? What's the catch?
That is the brilliant part of the design.
Okay.
The compute cost of a fully connected layer is tied directly to the dimensionality of its inputs and outputs.
Right.
Because the squeeze operation collapsed the spatial dimensions down to 1 by 1, these fully connected layers aren't operating on the massive H by W grid.
Oh, I see.
They are only operating on the channel dimension C.
Right.
Furthermore, the reduction ratio R creates a bottleneck.
How does that work?
If C is 256, the first fully connected layer compresses that down to just 16 channels, assuming R equals 16.
Then the ReLU.
Then they apply the ReLU, and the second fully connected layer expands it back from 16 to 256.
So it shrinks and then inflates.
Yes, and this bottleneck significantly limits the model complexity and the computational burden.
That makes sense.
We'll dive into the exact parameter math later, but keeping it mathematically lightweight is what makes this viable as a universal building block.
Taking that a step further, the bottleneck isn't just about saving compute, is it?
No, not at all.
By forcing the information through that lower dimensional space, the network has to learn generalizations about the channel dependencies.
Exactly.
It prevents the network from just memorizing a one-to-one mapping.
It has to figure out the underlying correlations between different feature channels to successfully reconstruct the 256-dimensional vector on the other side.
The math totally supports that intuition.
It forces the network to learn a robust mapping of channel interactions.
Okay, so it expands back out.
Now, after it expands back out, we hit a crucial mathematical choice.
The final activation.
The final activation function applied to these expanded weights is a sigmoid function.
Right.
This raises an important question. Why not use a mutually exclusive function like softmax, which is heavily used in other routing or attention mechanisms?
It's interesting they opted for sigmoid over softmax here for the excitation gating.
Very intentional.
Softmax makes sense for mutually exclusive class routing, but here we need the flexibility of multi-label feature activation.
Precisely.
We want the network to be able to simultaneously boost a texture channel and an edge channel without them competing in a zero-sum probability distribution.
Because multiple features can and should be important at the exact same time.
Right.
The sigmoid function treats each channel independently, outputting a value between 0 and 1 for each one.
Creating those weights.
It essentially creates a set of per-channel modulation weights.
So a score of 0.95
means this specific channel's features are highly relevant to the overall global context of the image, so amplify it.
And a score of 0.05
means this channel is acting as noise for this specific instance, so suppress it.
Okay, so we've got these global modulation weights.
We do.
But sitting on their own, they don't actually change the network's perception.
Not yet.
How do we mechanically fuse that back into the raw, uncalibrated feature map?
That brings us to step 3, the scale operation.
The scale.
The scale step is computationally very simple.
Okay.
We take our original h by w by c feature map, and we take our new 1 by 1 by c vector of modulation weights.
The outputs from the sigmoid.
Right. We simply perform a channel-wise multiplication.
Let's multiply them.
We broadcast the scalar weight for channel 1 across the entire spatial grid of channel 1 in the feature map.
So if a channel got a high score from the excitation step,
every single spatial pixel in that channel gets multiplied by that high score, boosting its signal.
And if it got a low score,
the entire channel is effectively silenced.
Wow.
This explicitly models the dynamic, nonlinear dependencies between channels using global information.
It's a remarkably elegant formulation.
It really is beautiful math.
But an elegant theory is only as good as its practical application.
Always the case.
In the world of deep learning, there is almost always a brutal compromise.
The trade-off.
If you want a more accurate model, you usually have to pay for it with massive increases in computational cost, memory usage, and inference time.
Usually, yes.
I remember when this paper dropped in 2017, half the machine learning community didn't believe the efficiency claims.
People were very skeptical.
There was a lot of skepticism that you could just bolt on these fully connected layers without tanking the training throughput.
Let's break down the exact numbers the authors reported to address that skepticism.
Let's hear the numbers.
A standard ResNet 50 architecture requires approximately 3.86 gigaflops to process a single 224 by 224 pixel input image.
3.86, okay.
When the authors added their squeeze and excitation blocks to every single residual stage creating the SE ResNet 50, the computational cost pushed to approximately 3.87 gigaflops.
Are you kidding?
3.87.
That is a minuscule 0.26% relative increase in computational compute.
It is practically a rounding error.
In the context of GPU utilization, it's nothing.
But the result you get for that tiny 0.26% tax is staggering.
It's huge. For that microscopic cost, the SE ResNet 50 completely outperforms the baseline ResNet 50.
Decisively.
In fact, its error rate drops so significantly that it actually approaches the performance of a much deeper network like ResNet 101.
And a ResNet 101 requires roughly 7.58 gigaflops.
Double.
Almost double the compute.
So you're getting the performance of a network that requires almost double the compute for 0.25% increase in floating point operations.
It is a phenomenal return on investment in terms of FLOPs.
How is the FLOP increase so small?
The reason the FLOP increase is so marginal is exactly what we discussed earlier. The bottleneck operations are taking place on a 1x1 spatial grid.
Right.
A standard 3x3 convolution in the middle of a ResNet block is performing math over a large spatial area, which dominates the FLOP count.
That's where all the math happens.
The SE block bypasses that spatial tax entirely.
Wow.
However, to be entirely fair and impartial to the skepticism you mentioned, we must also look at the parameter count.
The parameters.
Which tells a slightly different story than the FLOP count.
The parameter count is where the fully connected layers finally show their weight, right?
They do.
Because even though they operate on a 1x1 grid, a fully connected layer still requires a dense weight matrix connecting the input channels to the hidden channels.
Exactly. The squeeze and excitation blocks do add parameters.
How many?
For the SE ResNet 50, it adds about 2.5 million parameters.
Okay.
The original ResNet 50 has about 25.6 million parameters.
So we are looking at roughly a 10% increase in the parameter footprint.
Correct. While the computational time is virtually unchanged, the memory footprint during training and inference does increase.
A 10% parameter increase is definitely more noticeable.
Especially if you are deploying to memory-constrained environments.
Or dealing with strict VRAM limits during batch training. How did the authors address that trade-off?
They conducted a deep empirical analysis on where those parameters were actually being allocated across the network's depth.
Where were they going?
They found that the vast majority of these new parameters come from the final stage of the network.
The end.
Right. In a ResNet architecture, as you go deeper, the spatial dimensions shrink, but the channel dimensions double.
So they get really thick at the end.
By the final stage, you often have 2048 channels.
Right.
A fully connected layer operating on 2048 channels, even with a reduction ratio of 16, requires a significant number of weights.
Just mathematically.
But here is the critical discovery.
What's that?
The authors noted that the SE blocks in that final stage provide very marginal performance benefits.
They don't do much.
Right. If you strip the SE blocks completely out of just that last computational stage, the performance loss is less than 0.1% on the top 5 ImageNet error.
So almost zero loss in accuracy.
But the parameter tax drops dramatically from a 10% increase down to just a 4% increase.
That's a highly practical engineering insight.
It's huge.
They basically provided a roadmap for pruning the architecture for efficiency without sacrificing the primary accuracy gains.
And that level of relentless testing is a hallmark of this paper.
They really put it through the ringer.
They didn't just train one SE ResNet on ImageNet, declare victory, and submit the paper.
No.
They subjected this architectural block to an absolute gauntlet across different domains and baseline models.
They systematically proved that the SE block is a universal plug-and-play module.
Universal.
They tested it on CFAR 10 and CFAR 100, which feature much smaller, lower resolution images compared to ImageNet.
And the SE models consistently yielded lower error rates.
They took it to the Places 365 dataset.
Which is a massive scene classification challenge.
Right. Places 365 is notoriously difficult because it involves high intraclass variation and complex contextual clues.
Differentiating between a bedroom and a hotel room, for instance.
The SE ResNet 152 achieved state-of-the-art results there as well,
demonstrating that channel recalibration is highly effective for parsing complex global scenes.
And they also moved beyond classification entirely.
Right into object detection.
Using the COEC SEO dataset.
Right.
By just swapping the backbone of a faster RCNN detector from a standard ResNet to an SE ResNet, they improved the average precision metric by 2.4%.
It wasn't just making the model better at guessing the main subject of an image.
No, it was actually improving the feature representations used for bounding box regression.
And localizing multiple objects within a single frame.
If we connect this to the bigger picture of edge computing, what's truly impressive is their work with lightweight architectures.
Yes, this is key.
They integrated SE blocks into MobileNet and ShuffleNet.
These are architectures specifically designed under extreme parameter and computational constraints to run on mobile devices.
Tiny models.
Even in those highly optimized, highly constrained environments, adding SE blocks provided a substantial margin of improvement with minimal overhead.
This proved conclusively that squeeze and excitation wasn't just a brute force trick.
Right. It wasn't something that only worked when you had the luxury of massive server-grade over-parameterization.
It addressed a fundamental architectural deficiency in how convolutional networks process channel information.
It fixed a core bug, essentially.
Okay, so the empirical results are bulletproof.
Definitely.
We know the architecture works, and we understand the computational trade-offs. But I want to look inside the black box.
Let's open it up.
How did they arrive at this specific formulation, and what is the network actually doing mathematically with these new modulation weights? Let's dive into the ablation studies.
The ablation studies. This is where researchers systematically dismantle their own hypotheses to see what actually drives the performance.
Which is so critical.
It's crucial for separating the essential mechanisms from the incidental ones. The authors asked themselves a series of critical architectural questions.
Okay, like what?
First, why use average pooling for the squeeze step?
Right. Why not max pooling?
They tested it against max pooling, which takes the highest activation value in the spatial grid rather than the average. The results showed that while max pooling worked reasonably well and still improved upon the baseline, average pooling consistently outperformed it.
That makes intuitive sense if we go back to our crowded room analogy.
Let's hear it.
If you want to gauge the overall mood of a room, taking the average volume of all conversations gives you a much better global context than just finding the single loudest person screaming in the corner, which is essentially what max pooling does.
The math aligns perfectly with that intuition. Taking the average provides a smoother, more representative global statistic.
What else did they test?
Next, they revisited the excitation nonlinearity. We discussed earlier why they chose sigmoid over softmax to allow for multi-label, non-mutually exclusive activation.
Right.
But what about ReLU?
Oh, interesting.
They swapped the final sigmoid activation for a ReLU, and the performance completely collapsed.
Totally fell apart.
In fact, the error rate spiked higher than the baseline ResNet that didn't have any SE blocks at all.
Wow, but it makes sense. Using ReLU for the gating mechanism inherently creates a sparse activation map.
Which in this context means permanently dead channels for that specific forward pass.
Right, if the bottleneck outputs a negative value for a channel, ReLU clamps it to an absolute zero.
And when that zero is multiplied against the entire spatial feature map during the scale step, it completely obliterates that feature channel.
The gradient for that channel becomes zero,
effectively halting learning for that specific pathway.
That is the exact mechanism of failure. Sigmoid provides a smooth, differentiable curve between 0 and 1.
Allowing for nuanced scaling without entirely killing the signal.
And preserving the gradient flow during backpropagation.
They also tested TON, which outputs values between -1 and 1.
How did that do?
TON performed worse than sigmoid, further validating that a strictly positive 0 to 1 scaling factor is the mathematically optimal approach for channel recalibration.
You want to modulate the amplitude of the feature, not invert its sign.
Exactly.
They also explored the physical integration strategy. Where exactly in a ResNet block do you put this SE module?
A standard residual block has a main branch with a few convolutions and an identity shortcut branch that bypasses them, and then they are added together.
Right.
The authors tested putting the SE block before the residual unit, called SEPRE.
Okay.
They tested putting it in parallel with the identity connection, called S-identity. Both of those worked well, yielding results almost identical to their standard design, where the SE block sits right after the final convolution, the main branch, but before the addition.
But what if you put it after the summation?
Putting it after the summation, called SE post, actually degraded performance.
The degradation with S-post highlights a vital architectural nuance of residual networks.
It really does.
ResNets work so well because the identity shortcut provides a clean, unadulterated gradient path backward through the network.
The summation operation, f of x plus x, is what enables the training of ultra-deep networks.
If you place the squeeze-and-excitation block after that summation, you are applying a nonlinear scaling operation to the identity mapping itself.
You are recalibrating the main gradient highway, which disrupts the optimization dynamics that make ResNet stable.
By placing the SE block inside the residual branch before the addition, you are only recalibrating the newly learned residual features, f of x.
Ensuring that the primary identity flow, x, remains pristine.
Here's where it gets really interesting.
It does.
Beyond the architectural permutations, the authors actually sought to visualize what these learned modulation weights were doing.
They didn't just look at the loss curves.
They looked at the internal activations. They pulled sample images from the ImageNet validation set.
Specifically, they highlight a goldfish, a pug, a plane, and a cliff.
They then extracted the 1 by 1 by C excitation weights from different SE blocks across the depth of the network
to see how the channels were being modulated for these different images.
What did that layer-by-layer empirical analysis reveal?
They discovered a fascinating evolutionary behavior as the forward pass moves deeper into the network.
Let's examine the early layers first.
Okay, in the layers closest to the raw input image, like the early SE23 block, the SE blocks excite features in a totally class-agnostic way.
Agnostic.
If you plot the activation weights for the goldfish, the pug, and the plane, the distributions are nearly identical.
Wow.
All of the different image classes are triggering the exact same channel recalibration patterns.
That aligns with our fundamental understanding of deep learning feature hierarchies. Low-level features are universal. The network is essentially saying, at this early stage, regardless of whether I'm looking at a dog or an airplane, basic edge detection, Gabor filters, and color contrast channels are universally important to amplify.
The global context isn't highly semantic yet.
But as we move deeper into the intermediate layers...
As we move into the deeper layers, like the SE46 or SE51 blocks, the behavior shifts dramatically.
How so?
The blocks become highly specialized. The activation distribution for the goldfish diverges completely from the distribution for the plane.
Oh, wow.
The network is dynamically routing its attention based on the specific semantic content of the image it is currently processing.
So if the global pooled context suggests an aquatic environment,
it cranks up the scaling factor on channels that have learned to detect scales, fins, or water textures.
And if the global context suggests an aviation environment,
it suppresses those aquatic channels and amplifies channels sensitive to rigid metallic structures or sky textures.
The SE blocks effectively grant the network a dynamic input-conditioned routing mechanism.
They do.
But what about the very final layers, right before the global pooling and the fully connected classification head? Do the activations continue to diverge?
Actually, they observe the opposite.
Oh.
In the absolute final layers, specifically the SE53 block, they observed a distinct saturation effect.
Saturation.
The activation weights for almost all channels, regardless of the input class, saturate near 1.0.
Mathematically, if you multiply a feature map by a vector of ones, you are just applying an identity operator.
Right.
The scale operation does absolutely nothing. The SE block essentially turns itself off.
Exactly. And this empirical finding perfectly explains the earlier point we discussed regarding parameter pruning.
Oh, right.
It mathematically validates why they could strip the SE blocks from that final stage to save parameters without losing accuracy.
Because by the end of the network, the spatial dimensions are tiny.
Often 7 by 7.
And the features are already highly semantic and perfectly tuned.
The spatial and channel information is already so deeply correlated that no further explicit channel recalibration is necessary.
If we connect this to the bigger picture, this proves that SE blocks provide instance-specific responses to support the class-specific needs of the model as it gets deeper.
It's not just a static filter bank initialized during training.
It's a dynamic mechanism that reacts uniquely to every single forward pass.
And that localized self-attention leads directly into the lasting influence and legacy of this paper.
Because this wasn't just an architecture that won a competition and then gathered dust on a server.
No, it validated channel attention as a mandatory concept in modern neural network design.
Before ResNet, attention mechanisms in computer vision were primarily spatial.
Researchers were focused on figuring out where to look in an image.
ResNet proved that figuring out what to look at, which semantic channels to prioritize, was equally, if not more, important.
This heavily influenced subsequent multi-branch, attention, and transformer-based visual models.
A perfect example of that legacy is the CBAM paper.
The convolutional block attention module.
Which came out shortly after. CBAM essentially looked at ResNet and said, why not both?
Right.
They designed a module that sequentially applies channel attention heavily inspired by ResNet, followed by a spatial attention module.
It became another massive hit. ResNet opened the floodgates for that entire lineage of research.
Furthermore, Squeeze-and-Excitation became a fundamental atomic building block.
It stopped being viewed as a novel architecture and quickly became standard plumbing in deep learning libraries.
When researchers started developing neural architecture search, or NAS,
using reinforcement learning algorithms to automatically design optimal network topologies, like Google's ResNet and ImageNet.
They included SE blocks in the search space as a default primitive operator.
And the NAS algorithms consistently chose to incorporate SE blocks into their generated architectures.
Because the ratio of performance gain to computational cost is just so undeniably optimal.
It became part of the standard vocabulary of deep learning.
However, no paper is perfect, and we must analyze the limitations.
Fair enough.
The authors themselves were quite transparent about the engineering realities.
While the SE block adds minimal computational compute in terms of GFLOPs, it does add sequential depth to the network.
Right, those extra global pooling and fully connected layers mean extra sequential memory operations.
Depending on the specific hardware optimization, whether it's an NVIDIA GPU, a Google TPU, or an edge device accelerator, those sequential operations can introduce memory access bottlenecks.
That slightly impact real-world latency, even if the theoretical FLOP count is negligible.
Moreover, the authors defaulted to a reduction ratio of R equals 16 universally across the entire network.
Right.
While empirically sound as a default, finding the true optimal reduction ratio for every single individual layer rather than applying a blanket hyperparameter would likely yield even better results.
But doing so requires extensive, computationally expensive hyperparameter tuning that might not be feasible for every research team's budget. But despite those minor practical limitations, the legacy is incredibly secure. It is an absolute masterpiece of efficient architecture design.
It really is.
Which brings us to my absolute favorite part of the deep dive.
Here we go.
Welcome to Novel Notions, where we pitch outlandish but plausible new research ideas inspired by the paper's legacy. Please note, this segment is strictly for entertainment purposes only.
Do not go bet your startup funding or allocate your entire computing cluster based on these ideas.
Well, let's have some fun. We've seen how Squeeze-and-Excitation revolutionized computer vision by compressing global context to dynamically gate specialized channels. What if we drag that core philosophy into the present day, outside of vision entirely?
I like the direction. The most pressing frontier right now is large language models, specifically the scaling challenges of mixture of experts or MoE models.
Let's run with that. Idea 1, cognitive squeeze and excitation for mixture of experts LLMs. In a standard MoE model, you have a router network. It looks at an incoming token and makes a hard routing decision, sending it to, say, the top 2 experts out of 8 available experts.
It's an isolated, token-by-token routing mechanism.
How would we translate the SE mechanism into this text-based architecture?
The technical translation for this requires rethinking what a channel is in an LLM.
Right.
Instead of visual channels, our channels are the distinct expert models.
The coding expert, the creative writing expert, the math expert, the logic expert.
Exactly. First, we need the squeeze operation.
Instead of spatial dimensions, we have the sequence dimension of the prompt.
Imagine a user provides a complex 2,000-word prompt containing Python code, a request for historical analysis, and a creative writing constraint.
The huge prompt.
We take the hidden state embeddings of that entire sequence and apply a temporal squeeze.
A global average pooling across the sequence length.
This collapses the 2,000 tokens into a single, dense, global context vector that mathematically represents the overall vibe or complex intent of the user's entire request.
And then we apply the excitation network to that global context vector.
Right.
But rather than using a standard softmax router to force the prompt into the top 2 experts, which is mutually exclusive, winner-takes-all routing, we use the SE paper's sigmoid activation.
We pass that global context vector through a fully connected bottleneck, and it outputs continuous modulation weights for all the expert models simultaneously.
This completely alters the routing paradigm. By using a sigmoid activation over the experts, you apply a continuous recalibration scale to the entire mixture.
It allows for a non-mutually exclusive blending of agent outputs based on the global prompt context, rather than greedy token-level routing.
If the prompt is, write a Python script that generates a Shakespearean sonnet about vector calculus,
the network doesn't have to arbitrarily choose between routing to the coding expert or the creative expert.
the squeeze and excitation routing layer analyzes the global context and outputs a 0.95 for the coding expert, a 0.85 for the creative expert, and a 0.70 for the math expert,
while suppressing the legal expert to 0.01.
It dynamically recalibrates the mixture based on a globally pooled understanding of the entire prompt. The first experiment I would run is taking a standard open source MOE, swapping out the top pair router for an SE bottleneck router with sigmoid activations, and benchmarking it on multidisciplinary reasoning tasks to see if it reduces context switching penalties.
The memory bandwidth requirements for activating all experts with continuous waits might be challenging, but from a theoretical standpoint, it perfectly mirrors the channel recalibration logic of the original paper.
Okay, idea 2 is a bit more visual, tying back to the paper's roots, but applying it to the cutting edge of generative AI.
Let's hear it.
Idea 2, temporal squeeze for hallucination prevention in video generation. The current models generating video suffer from massive temporal hallucinations. The model generates a consistent frame, but a few seconds later, a car drives behind a tree and emerges as a totally different make and model.
Or a person's jacket spontaneously changes color from red to blue between cuts.
The model fundamentally loses the global temporal context.
It's a major unresolved issue in diffusion models and autoregressive video generators. They struggle with long horizon consistency.
Right?
How would you apply squeeze and excitation to establish a baseline truth across the sequence?
We apply the SE blocks across the temporal dimension. Think about the output tensor of a video generation model. It's no longer just H by W by C.
It's T by H by W by C, where T is the number of frames over time.
The technical mechanism here is that the network squeezes the global average pooling of all generated frames over the entire temporal sequence.
We aren't just squeezing the spatial width and height of one frame.
We are collapsing the entire timeline of the video into a single global physical context vector.
I see the architecture. It's extracting a baseline semantic truth for the entire sequence. The pooled vector essentially encodes the structural invariance of the scene. This video contains a subject wearing a red jacket, driving a blue sedan.
And then it uses the excitation network to push that global temporal context back into the spatial generation layers of the current frame being rendered.
It uses that global vector to excite specific spatial features in the local frame to ensure consistency.
The global squeeze says, hey, across the macroscopic view of all 60 frames, the red jacket channel is highly active. Therefore, when generating the pixels for frame 45, the excitation network dynamically boosts the red jacket channel and heavily penalizes the blue jacket channel.
You're forcing the local generation to that specific frame to adhere to the global temporal context of the entire video. The beauty of that idea is that it leverages the exact computational efficiency we analyzed earlier. Adding a temporal SE block would add an incredibly microscopic amount of GFLOPs to the video generation process, which is already astronomically expensive. But it could entirely stabilize the temporal consistency.
You're effectively giving the video generator a lightweight, globally aware memory buffer that mathematically punishes object morphing.
It's all about using global information to recalibrate local decisions, which is the eternal lesson of the Squeeze and Excitation paper.
And that brings us to the end of our deep dive today.
It's been a fun one.
But before we go, I want to leave you with a final provocative thought to mull over. We've seen today how a brilliantly simple mathematical operation, just taking the average of a grid of pixels to create a global scalar, can give a neural network enough structural self-awareness to recalibrate its own feature channels and achieve state-of-the-art performance.
Very true.
But if a simple global average pooling operation can do all that, what happens when we replace that simple mathematical squeeze with a secondary, smaller neural network whose only job is to psychologically profile the incoming data stream? Could the next evolution of squeeze and excitation be models that don't just mechanically weigh their features, but actively internally debate their relevance using a secondary critic network before making a final routing decision?
That's a powerful thought.
Think about that next time you look at a feature map, and we will see you on the next deep dive.